Good afternoon, everyone. My name is Gareth Leonard. I'm the Managing Director for REGENESIS in Europe. Sorry if anyone was online there for our technical glitches at the start. I have a new computer, and as you'll know, the newer the computer you have, the less connections you actually have. So it was a bit of a scramble at the start, but we're there now. For those of you who don't know REGENESIS, we provide injectable substrates for the remediation of contamination in situ. We are based around an R&D department, very talented people based in California, and what they do is they develop technologies to solve issues for brownfield sites. We then take those to the market, and we work with end users, we work with remediation contractors, we work with consultants, we work with regulators in order to solve brownfield contaminated groundwater issues. We're always looking at trying to improve things. And today we've got a couple of technologies that have launched quite closely together. They're very, very different products, but we've put them together today because they both treat high levels of contamination. One particularly focuses on chlorinated solvents, the other on petroleum hydrocarbons, and they use very different approaches. So normally this would be two webinars. I've put them together as one webinar, so we'll be covering a lot of ground today, but hopefully we can give you an insight. And if you have any further questions or need any more information, we can send those to you, or you can go to our website where we have a lot of technical bulletins. Okay, so the pointer's not working. We'll try this. No, okay. Bear with us for a minute. There you go. Okay. So this is what we're talking about today. The first product is called S-MicroZVI or ZVI. I'll find myself slipping into the American term because I do deal with our American colleagues quite a lot. I'm also going to be misspelling sulfidated all the way through this, so I apologize to the British English people speaking people out there. The second product I'm going to be coming on to after that is a product called PetroFix, which is a dual action product relying on sorption and then biological degradation to treat medium to high levels of contamination. Throughout, I'll be showing examples from the laboratory or beta test sites, and then hopefully there will be questions, time for questions at the end. If there isn't, if I don't manage to get round to answering all the questions, then we will get back to you, as Amanda said. So, first product, sulfidated colloidal zero-valent iron for groundwater remediation. Now, quite a few terms in there already, so a lot of you will be up to speed, many of you won't on some of these terms, so I'll try and explain these as I go through, okay? So what the product does is it gives you in situ chemical reduction. So this is a term that's been used since the 1990s. It covers a number of reactions, but essentially it is remediation technologies where the remediation occurs primarily through chemical reduction of the contaminants. So it's a chemical reaction and it's reducing the contaminants. So the emphasis is on the abiotic, so the non-biological side of things. The reductant, whether it's naturally occurring or in the case we're talking about today, what we're applying, causes the reduction of the contamination by supplying electrons. So it's a redox reaction, oil rig, oxidation is loss, reduction is gain. And the contaminant accepts the electrons. So in the case I put there, trichloroethylene, TCE, loses chlorine and gains hydrogen in that process. Oops. So it can occur naturally. So if you've got anaerobic conditions, you might have some reduced iron in the system and you're having this abiotic degradation going on. It can occur with less reduced intrinsic, they call it, metals, if you are doing biostimulation. So if you have put in an electron donor and you are doing enhanced biological degradation in anaerobic conditions, those anaerobic conditions can create reduced varieties of metals such as manganese and iron, and you can get abiotic degradation of the contamination as well as the biological degradation you were aiming for. But what we're going to be talking about today is the addition of strong chemical reductants. So this is an engineered product that we put in the ground specifically for reducing that contamination. So we're talking about zero valent iron, ZVI or ZVI. What is zero valent iron? It is one of these strong engineered reductants. It doesn't occur naturally. Iron typically exists as Fe2 or Fe3 in the reduced and oxidized forms in the groundwater, variously depending on the redox in the groundwater itself. Fe0, zero valent iron, is a manufactured product. So very pure, very little else in there except the iron, and it has been reduced so that it is ready to give away electrons. It's very reactive, and it wants to reduce matter in the groundwater. And indeed, as I'll come on to, it actually will react with the water itself in order to give away these electrons, which we'll touch upon. So what are we trying to improve upon? Why have we created a zero valent iron particle? What are we doing? So it's been around since the 1990s. There are challenges with the technology. The reactivity, as I mentioned, it's very reactive. It even wants to react with water. So we want that reactivity. We want it to react with the contamination. But if it's too reactive, then it doesn't last. It doesn't get a chance to degrade the contamination. And because it's a chemical reaction, it's a contact sport. In the same way that you think about chemical oxidation, okay, not quite the same way as you think about chemical oxidation, but direct chemical oxidation, you need contact with that contaminant, okay? So that leads on to persistence. If it's too reactive, it's not persistent. You want something to last in the groundwater, so it's got a chance to work on the contamination, particularly if you're using a barrier, so you're wanting the product to last, so contamination moves into that barrier and is treated. Equally, if it's not reactive enough, and so it's very persistent, you have a product that's sitting in the ground for a long time, but it's not actually doing the remediation that you want. Delivery has always been an issue with zero valent iron. It's very difficult to get zero valent iron to move through the pore throats, generally because of the size of the particle. It's heavy, it's iron, it settles out. You often have people making suspensions of it using the likes of guar gum. So you're having to fracture it into the formation, which can cause issues. So this is something we wanted to try and improve upon as well. And then the ease of use. How easy is it to inject? Do you need high pressure? How safe is it to use? As we'll come on to, powdered zero valent iron can cause dust hazards, potentially explosion hazards if you're using it inside. So it's something, the health and safety side of things is obviously something that we wanted to improve on as well. So the idea is we result in a significant improvement in the efficacy, the utility, and the economy of using the product and using the technique. So S-micro zero valent iron. S stands for sulfidated. Micro is the scale, so it's near micro scale. So it's less than 5 microns in diameter, all the particles, and then it's a zero valent iron. So that's what the name means. It's quite a complex name, but trying to get all that information in there. So it's an engineered zero valent iron product. It's colloidal. So there's another term. So colloidal is a suspension. It's a true liquid. So if you have colloids, they are particles generally suspended in water. So milk is a colloid, wine is a colloid, blood is a colloid. In this case, we've got zero valent iron as a colloid floating in water and glycerol, which I'll come on to. So the particle size is less than 5 micron, so near micron, micro scale zero valent iron. That's made in our facility in Oceanside in California, where we mill the product down to that size. We then sulfidate the particle. We cover the particle in iron sulfide, which I'll come on to. And then finally, we coat the product in glycerol. It's within a glycerol suspension. So this combination gives you abiotic degradation, and it also gives you something called ISCR enhanced biological degradation. So that is the process whereby in situ chemical reduction also helps the biological process along, and I'll cover that too. So the benefits of the product are that when you use it, you get a reduction in daughter products. So instead of going through dehalogenation of chlorinated solvents, where you'll move through more toxic biological products, there is something called the beta elimination pathway, which will take you through acetylene and onto ethene and ethane. So the amount of breakdown products that you're getting will be reduced. The product itself, because of the size of it, will fit through pore throats very easily. And because of the suspension, we can move it through the formation with low pressure injection. So it has very good distribution. It's always been an issue with zero valent iron that you can't get it to move very far. That's why you tend to see iron in PRBs, that's permeable reactive barriers, where it's in soil mixing, etc., because you're not able to get the product to flow through the subsurface, and we've managed to do that with this product. It's very easy to use. When you get it to site, you're just adding some water, diluting it, and then you can shoot it into the ground, or you can add it into the electron donor substrate that you're using to give enhanced reductive dechlorination, and just shoot it under the ground under low pressure injection. It gives enhanced reactivity with the contaminants, about 10 to 30 times that of a commodity zero valent iron, so it's highly reactive, much more so than commodity zero valent ions. But at the same time, we've managed to get it to persist for a very long time. So we've minimized the reaction with water, and the product is persistent for around about 2 years, we think, with this increased reactivity as well. So it's in a real sweet spot in terms of the different things it brings to the table for treatment. So treatable contaminants, a lot of what we'll be treating with this product is chlorinated solvents. Mostly you get them from dry cleaning sites and industrial sites. These were generally within the process of the cleaning, or they were disposed of at the back. There's a lot of the time when you see these plumes from sites where it's not a spill, they'll have had a place at the back of the site where everybody knows the chlorinated solvents volatilize, so they'd go and dump them out the back thinking they'd just volatilize to the air. But actually, they're also very good at sinking, getting into the groundwater and causing widespread contamination. So chlorinated solvent plumes from dry cleaners, also from industrial facilities where they're used as degreasing agents. Chlorinated ethanes, they are also used as degreasers, but also they can be intermediates and stock for other chemicals. Zero valent iron can break down these chlorinated ethanes in the presence of chlorinated ethenes, which sometimes can slow down and inhibit biological degradation, so there's an advantage of using them then. You can degrade pesticides like lindane. You can also treat things like chrome-6 through stabilizing these metal oxyanions. So where you've got electronics manufacturing, adhesives factories, etc. And also where you've got the nitro reducible functional groups, so you've got accelerants, so military facilities, etc., energetics, we can treat that with zero valent iron too. So 4 cornerstones of successful remediation using zero valent iron are reactivity. We want good reactivity. We want to break down that contamination. We want persistence. We don't want it to disappear too quickly. We don't want it to be too persistent so it's not reacting. We need it to be easy to use, safe to use, and we need it to distribute in the subsurface so that we're not having to backfill trenches, that we're not having a soil mix. You can just inject it into the subsurface. So if we take those one by one, if we look at reactivity at first, we'll look at the abiotic reduction that I was talking about. Now, the reaction pathway along the top there is dehalogenation, reductive dechlorination of chlorinated ethenes. So the tetrachloroethene on the left there, the PCE, will break down through biological means, through dehalogenating bacteria, through TCE, through DCE, through vinyl chloride, to ethene, where it's fully dechlorinated, at that point it will then mineralize to ethane and eventually carbon dioxide and water. And that's fine, it works very well. We do that all the time. The advantage you get with zero valent iron is that bottom pathway, in that the PCE and TCE particularly are susceptible to degradation through the beta elimination pathway. So you'll break them down through into the acetylenes, and then those acetylenes break down into ethene and then full mineralization. So what you find is if you've got a plume of PCE and TCE, if you add the zero valent iron, you'll still get the biological degradation, but what you tend to get is less daughter products being produced, which is a real advantage. You know, it keeps the risk from the plume as the remediation is evolving to a minimum, and it also reduces the program length for hitting targets. Sulfidation is used because of the reactivity of zero valent iron. So zero valent iron is very reactive. You put it into water, it will react with that water and produce hydrogen, okay? So that results in passivation. So basically you've spent money on this product to deal with the contaminant itself. You put it into the water and it breaks down the water itself, producing hydrogen. So that means you are not getting an efficient treatment of the contamination. You're producing hydrogen, which may drive reductive dechlorination, but in extreme cases can produce hydrogen, which is problematic for the site, but that's an extreme case. It decreases the persistence, so you don't have the product lasting as long. And as I say, less treatment of the contamination. So the answer is to sulfidate the ZVI surface. So what you do is coat the surface of the zero valent iron in a sulfide, in this case an iron sulfide. So you're corroding the surface, you're putting an iron sulfide onto the surface, and what that does is it limits the reaction with the water while not limiting the reaction with the chlorinated solvents. So this is an increase in the electron efficiency. So the electrons that are available from zero valent iron, where are they going? It's efficient if they're going to the contaminant. It's not efficient if they're going to the groundwater itself. So if you look at this work, I've taken this from Dr. Paul Tratniak from Oregon Health and Science University, and he showed this in a presentation on sulfidation. He's also got a chapter in the one of the SERDP guidebooks as well, which I can pass on the reference to at the end. What he's quoting here on the left is some work by Dimin Fan. What you can see is electron efficiency on the left, and he's got NZVI, so that's nano zero valent iron, so that's very small scale zero valent iron. And what you can see in the purple column is that nearly all of the electrons from the zero valent iron are being used to break up water. And the little red column is the TCE, the trichloroethylene. So it's very inefficient. It's all being used to break up water. Now on the right, with the sulfidation coating of the particle, you can see that the opposite is true. There's very little degradation of the water, and you're degrading, all the electrons are moving to the TCE, to the chlorinated solvents that you want to break down. The work on the right there, if you look on the right, you've got the zero valent iron. It's got an iron oxide coating on the surface. As the reaction with the water and the contamination occurs, you get these oxides being produced. But if you look at the thick red line, wiggly line, it's got 92%, and that's pointing at a reaction producing hydrogen. So 92% of the electrons are coming from the zero valent iron, and they're reacting with the water to produce iron. If you look at the left side of that semicircle where we've got sulfidation, and look at that thick red wiggly line at the bottom, it's going via the sulfidation, and it's treating TCE there and breaking down the contamination with very little going to the water itself. So there's some really nice studies on sulfidation that I can pass on at the end if you just want to email in or type in the comments box, and I can pass those on. But basically what it does is it really directs the electrons towards the contamination. So as well as this biotic abiotic degradation of the contamination. What the product is also doing is giving you ISCR-assisted bioremediation. So as a reminder, enhanced reductive dechlorination, you would put in a controlled release donor, and often we use this zero valent iron product with this molecule here, which is 3D microemulsion. So you put this 3D microemulsion into the ground. First thing it does is dissolve. That dissolution then results in organic acids being put into the groundwater. The organic acids will then ferment. It's a two-stage biological process. As the organic acids ferment from lactic acid to pyruvic acid to acetic acid, the breakdown product is hydrogen, dissolved hydrogen, which the fermenters don't really care about. But that dissolved hydrogen is then used by dehalogenating bacteria, reductive dechlorinators. So through hydrogenolysis, they break down the contamination, as I've discussed before, PCE, TCE, DCE, vinyl chloride, ethene, etc. Where zero valent iron helps, and bear with me, it's been a little bit slow because I've put some animations on. Where ISCR enhancement helps is that it can rapidly create anaerobic conditions, so the onset of this biological process will happen much more quickly. It will remove the dissolved oxygen, so again, you can get down to low redox conditions to drive reductive dechlorination. And also, there's glycerol in the product. There's glycerol in the S-MicroZVI valent iron. That will also ferment, provide hydrogen, and drive reductive dechlorination. So this means that you're able to address a greater mass. So you can, when you're looking at a chlorinated solvent site and you're looking at high concentrations, you might have been considering enhanced reductive dechlorination. You can push it further. You can take it further by adding S-MicroZVI valent iron into the mix, and these two processes will work together, the abiotic and the biotic, in order to degrade those high levels of contamination without giving you problematic daughter products and finishing the project in a sensible time frame. So this is a column study from our laboratory where we were looking at ISCR-assisted bioremediation. So the column on the left, we've got a sodium lactate, we've got some microbes in there, and we've got some contamination in there. And what you see is that you get biological degradation going on, you get dehalogenation. So the TCE breaks down and you get the DCE increasing, that's that orange line. And then as the TCE is broken down, there's no DCE being produced, so the DCE starts to come down, and you can see that that's heading down. And then the vinyl chloride is produced, and that will start to go down as well, and that'll be the end of your project. And so that's fine. But then if you look on the right, if you then add the zero valent iron into the mix, what you're getting is rapid reduction of that TCE. It's biologically breaking down as well, but you're getting rapid abiotic degradation of it. So there's less TCE available to create DCE. So that TCE is removed immediately. You do get DCE being produced, but you can see it's much lower. You get vinyl chloride being produced because of the biological degradation, but it goes down to zero much quicker. So you're just getting through that contamination much more rapidly. So that was reactivity. Looking at distribution, the fact that the S-MicroZVI valent iron is a small particle, less than 5 micron in size, means that they are much more buoyant in the groundwater. You can suspend them much easier. So when you come to site, you get a concentrated mix, you'll mix it with water, or you'll mix it with the 3D ME and shoot it into the ground. Under low pressure, it will then be distributed through the pore throat. So it'll just be pushed with low pressure, and it'll go quite far. You know, if you were injecting the zero valent iron by itself, you might be on something like a 3-meter injection grid, something like that. And that, perhaps to some of you, doesn't sound really that far, but compared to where zero valent iron used to be, and using some other grades and types of zero valent iron, it's a massive step forward. It is a huge step forward. I still remember walking through our R&D lab and Kristen just saying, oh yeah, that's our zero valent iron going along a column, and the column was, 1.5 meters long, and it stopped me in my tracks. I was like, that's not possible. That was a few years ago now. So it really does go far for a zero valent iron. If you're using a larger particle size, they're not going to go through the pore throats. They're heavy. So you can see here with these 2 jars, you just get settling of the product straight away. And that'll happen in the subsurface as well. It's not going to go very far after your injection pressure has gone off. And so it settles down. So hence people use things like guar gum or maybe organic polymers, something that will break down in the subsurface to try and drive it out further, to try and create a thick suspension. Because it's thick, you need higher pressure. Because they're larger diameter products, you need to force them through the pore throat, so you have to fracture the subsurface. So you're not getting the product into the right place. Where you want to get the product into is the flux zones, into the permeable formation, the mobile porosity. You put the product into there, you deal with the contamination that's in there, you deal with the contamination that's moving through those flux zones and being degraded, and you deal with the back diffusion that comes out of the immobile porosity into these treatment zones. Fracturing, you're going to put the product in the wrong place. So a little bit more on that. I think I got ahead of myself there. If we look at characteristics of colloidal iron at the top there, if you look at that S-MicroZVI valent iron just being simply poured into water, you can see it blooming, is what we call it. It's just spreading out, it spreads so easily in water. On the right there, you can see a sandbox demonstration where you're getting plug flow. So it's filling that mobile porosity. You're just pumping under low pressure and it coats the subsurface. It spreads through the subsurface with this product. And the more you spread it through these flux zones, the more contact you're going to get with the contamination and the more efficient your remediation is going to be. If you look at microscale iron, now I know we talk about micro, but we're talking about far microscale ions, so something like 40 micron in size. They often have to be made as a slurry. You have to fracture them into the formation as I talk about. So you are going to get emplacement in the wrong locations, not necessarily where the contamination is located. So ease of use, the product comes in 200-litre drums. Comes as a fluid suspension, looks like that. It's basically pumped or poured into a mixed tank and diluted on site. Hopefully this video will work. I've pressed the button, but we'll see. It's working. Okay, just not on my screen. I'm getting the thumbs up at this end. So hopefully what you're seeing is the product just being poured into water, and then there's a mixer in the middle, and it's just spinning that round. And you can see how easily it mixes. Very low viscosity, similar viscosity to water upon injection, and then into the subsurface under low pressure. So you're using simple mixing and pumping equipment, very safe to use, no need for handling powder on site, so there's no dust or explosion hazards. There's no thick slurries to fracture the formation, just very, very straightforward on-site activities. So, persistence. So we talked about it before, that sulfidation gives you an improved electron efficiency. So you're getting much more persistence. The product lasts a long time. You've got a reduction in passivation. Here is a lab test showing that. So what we've got here is time on the x-axis and the mass of PCE on the y-axis. And this is a full extraction of the soil, the PCE in the soil and water within the test. So it's not the micron per milliliter, it's the amount of moles, it's the amount of mass that they're pulling out of the entire system. So there's nowhere to hide in this test. So what they're doing is every 2 weeks about going into the test and spiking the groundwater with PCE. So theoretically, the concentration should increase over time. This is the control, so you can see we're getting some losses in the system for whatever they may be, but you've got an increasing trend over this 150 days. When you've got the S-MicroZVI valent iron in there, the concentrations don't increase. And remember that it's not that this is adsorbing or being hidden. This contamination is now not in the system. So it is being broken down, and it continues to be broken down. There's no reduction in the efficacy, there's no reduction in the efficiency of the treatment over this 150-day period of the test. So I just want to go into different particle sizes and why we've chosen this scale for our product. So if you look at the different types of zero valent iron that are available, we've got soluble Fe2 on the left, so that is a liquid, so it's dissolved in the water. Then you've got nanoscale, you might have heard of N zero valent iron is 0.2 micron. Where we are is near microscale colloidal zero valent iron, 1 to 4 micron. And then far microscale powdered zero valent iron is commodity, and then you get on scrap iron, yet basically scrap metal that's crushed up and put in the ground. So in terms of kinetics, in terms of reactivity, it is about contact, it's about surface area. So the more soluble, the smaller the product, the greater surface area that's exposed to the groundwater, the more rapid you're going to get reaction. However, the opposite is true. Because you're getting that rapid reaction, they don't last as long. So the soluble material is great, but it doesn't last particularly long. At the other end is scrap iron, which is unreactive, but will sit there essentially forever. And we're sitting in the middle of that. Transport, the movement of the product through the subsurface, a little bit more complicated. You see, you start from the left high, and then you get to the right low. But there's a lump there in nano, and I know there's a lot of bright people trying to overcome this issue, but essentially around about that scale of product, you're getting agglomeration. So you might have a tiny particle size, but the agglomerate into larger particle sizes, which are then difficult to move through the formation. So where S-MicroZVI valent iron sits at a sweet spot, we feel, where you're getting good reactivity, it's long lasting, and it's easy to transport into the subsurface. In terms of how the products are applied, this is a list again from soluble at the top down to scrap iron. And you see the different sizes, how they're made through chemical precipitation. Our product is made through grinding, through milling. In terms of application, the smaller scale products can be injected through screened wells or direct push, and our product can be injected and has been applied in both. And then for these larger products, you tend to be doing soil mixing or backfilling into trenches. So the product can be applied by itself. More often than not, though, it's applied with an organic substrate like 3D microemulsion. You might apply microbes as well. It's also compatible with PlumeStop, our colloidal activated carbon product. Just to confuse you, it's not the activated carbon product I'm about to talk about, but it's one that is compatible with chlorinated solvents. And here's a quick lab test just showing the effect where you combine zero valent iron and the colloidal activated carbon. There's the PCE control. Again, it's a full extraction. And then when you, the biotic control, so we've got biological degradation going on. You see some reduction over 5 weeks. Where you have biotic degradation, so here we'll have sorption of the contamination on the PlumeStop, biological degradation of that contamination, and also abiotic degradation of the contamination via the zero valent iron. You get a rapid reduction right from the start. So S-MicroZVI valent iron, it can deal with a wide range of contaminants, particularly chlorinated solvents. It's got an unsurpassed combination of reactivity, persistence, distribution, ease of use. It's very useful where you've got high levels of contamination, and it can integrate with using PlumeStop and with electron donors. Okay, activated carbon amendment for petroleum hydrocarbons. This is PetroFix. This product has dual function. So now we were just talking a lot about treating chlorinated solvents. Now we're talking about treating petroleum hydrocarbons. You can't use this product for using chlorinated solvents because of the part of the product has sulfates in that, and it will inhibit the biological degradation of those chlorinated solvents. So if you're looking to use activated carbon with chlorinated solvents, and you're much better moving towards the zero valent ion, the plume stop side of things. So this is for petroleum hydrocarbons. It consists of a microscale activated carbon slurry. It is milled down to 1 to 2 micron. So that's the size of a bacterium, it's the size of a blood cell. It's a very, very fine activated carbon particle. And it's mixed with a slow release sulfate electron acceptor. There is then what we call the EA addition, the electron acceptor. I nearly did it myself, the Environment Agency addition, the electron acceptor addition, which has nitrate and sulfate electron acceptor mix in there as well. This, when applied to the subsurface, gives you a rapid sorption of the mobile contamination. So it will take the dissolved phase contamination out of the groundwater and sorb it to the activated carbon, and then it'll facilitate the onset of natural biological degradation. It'll kickstart natural attenuation of this contamination and allow that to continue on. So it targets petroleum hydrocarbons, BTEX, MTBE, naphthalene, etc. So 1 to 2 micron carbon, as shipped, it's 30% carbon in a 181 kilogram drum. We're actually starting to produce it in smaller drums as well, about 18 kilogram drums, and that's because we're being asked, particularly by domestic oil spill contractors, people who are sort of first responders to spills, to provide it in smaller SKUs, smaller quantities that can be just kept in the back of the van to respond in this way. And then there's a bucket that goes with it that has the electron acceptor blend. Now, typically we'll be providing it with an ammonium sulfate and sodium nitrate blend. And I'll come on to why that is. We want to get the microbes working together. However, there's going to be aquifers, there's going to be regulators, there's going to be situations where you don't want to be adding nitrates to the groundwater. So you can also just get a sulfate-based blend. Okay. Hopefully that's moving forward. Are we on to the next slide, Amanda? Okay, bear with me. Here we go. So the first thing that happens is you inject the product into the subsurface. It will spread out anywhere between 0.5 meter to 1 meter. If you've no fines, if you're putting into pipe bedding, etc., you might get it further than that. Bedrock, you might get it further than that as well. And what it does is it coats the subsurface. So you're getting this, these tiny particles of activated carbon to coat the aquifer itself. So if you look at this scanning electron microscope picture, you can see the scales 0 to 20 micron. This is actually pictures of activated carbon attached to the sand itself. And then what happens is the contamination basically is adsorbed onto activated carbon. Activated carbon is very good at adsorbing organic material into it. The second step is the biological degradation using nitrate and sulfate as the electron acceptors. And so this is anaerobic biological degradation. If you look at a plume of petroleum hydrocarbons in the groundwater, what's generally happened is it's gone anaerobic. It's used up all the oxygen, and then the microbes are using up the nitrates, the iron, the sulfate, and you might even have methanogenesis going on. So this is what a typical plume might look like. And what we want to do is stimulate degradation of the contamination through something called syntrophy. So you're getting different microbes working together, either alongside each other or one after each other, passing on the degradation products to each other to keep the process going and to keep the process efficient to biologically degrade that contamination in the groundwater. So I will come back to that, but I'm going to get there via talking about the challenges to bioremediation, where you've got high concentrations of petroleum hydrocarbons in the ground, and why really they persist in the natural environment and what we have to overcome. So inhibition of biodegradation is caused generally by 3 things. So high concentrations of hydrocarbons, a lack of terminal electron acceptors, and the buildup of inhibitory intermediates such as hydrogen and acetate. So the first one is something that I'm sure many of you are aware of, that if you have very high concentrations of petroleum hydrocarbons in the aqueous phase, it becomes biotoxic, even to those microbes that feed on this contamination, that they are unable to survive in those conditions because of the amount of contaminant that is there. So how PetroFix deals with this is by removing the contamination from the aqueous phase so that the microbes living in the aqueous phase do not suffer, but the contaminants are in contact with the aqueous phase, so they are bioavailable. The microbes can pull those contamination off and break that down, but they're not living amongst it. The next one is the lack of terminal electron acceptors. In this natural environment, the amount of electron acceptors within the plume itself will become depleted, and it's very difficult for these electron acceptors to then get into the plume, because around the edge of the plume, around the corona of the plume, you're getting this biological degradation occurring, but it's all being used up at this corona, and in the center you're getting very little going on. So what we'll do is biostimulate the degradation by adding nitrate and sulfate. There's benefits of this combined use. So the syntrophy, and here you probably can't read it, there's a reference to a good paper on syntrophy. There's a link to our website at the end of this as well. We've written a technical bulletin on syntrophy where we go into a lot more detail on this, and then there's reference to some papers on it as well. It's really interesting stuff, and the understanding is developing here as well. Nitrate is better for the degradation of benzene as well, so that's why we want you to use nitrate if you can as the EA blend in the product. So we put these terminal electron acceptors into the subsurface, into the plume itself, and stimulate biological degradation in anaerobic conditions, and you get this syntrophic effect. Now, the buildup of inhibitory intermediates is basically when you get the fermentation of the contamination. So here we have BTEX and TPH, and they're being fermented into carboxylic benzoic acid, and they eventually end up as hydrogen or acetate, low molecular weight acids. Now, thermodynamically, at the start, it's favorable. There's not much hydrogen, there's not much acetate, because not a lot of biological degradation is going on. So although it's biologically mediated, the reaction of breaking down that BTEX or TPH down to acetate, there's a big difference thermodynamically. There's a lot of energy there to be released. As the process goes on, as you're getting sulfate reduction, nitrate reduction, you're getting a buildup of hydrogen and acetate. So the concentration gradient decreases because you're getting this buildup of these intermediates. And so it's less thermodynamically favorable to degrade this contamination. So it's holding the process up. Now, the next link in the chain is methanogens. These archaea will break down the hydrogen and the acetate into methane, which is a naturally occurring process. All of these plumes will be producing a little bit of dissolved methane. So it's a matter of stimulating this process so that you hand off the intermediates to break them down, to keep the initial breakdown going on. So this syntrophy is all of these microbes working together. There's some interesting work done on how sulfate-reducing bacteria are quite adaptable. So if there's no sulfate, they can actually work with methanogens to continue their work. So it's really interesting stuff. There's some reference work down there, but the idea is that we kickstart this biological process, and then it can keep going with just naturally occurring electron acceptors in the future, and the process just continues on. So application. The product comes to site in drums, or it's going to be shortly in tubs as well. You mix it up, dilute it to the injection concentration you need, add in the nitrate sulfate mix. So you just simply pour those in together. and then it can be applied into an excavation, injected through direct push injection, injection through wells. Again, it's low pressure, there's no fracturing needed. These are tiny particles that can pass through the pore throat. You just want to put them into the flux zone. It's very safe to use as a non-hazardous product. You know, it's an activated carbon. You've got some in your kitchen for filtering water, etc. Or maybe that's just me. And you know, it's very easy using, just standard PPE required. So here's a couple of sites from the UK where they're using it on domestic oil spills. Easy. So looking at low pressure injection versus high pressure injection, you'll know about granular activated carbon. It has a large diameter, up to 1,000 micron. So to get that into the subsurface, you'd have to fracture it into the ground. Powdered activated carbon, you might have seen it for treating vapors. Smaller in diameter, but still 50 to 150 micron. It will agglomerate if you put it in together. It's still going to need fracturing into the formation. What we do with the PetroFix is we have a much smaller particle size, so it will fit through the pore throats. You can inject it at low pressure, less than 2 bar. There's no need for aquifer fracking, so you're not creating new pathways through the aquifer. You're not fracturing the product directly to the well and ruining the monitoring wells. You're coating the subsurface. You're coating those flux zones. There's some example of pore throats diameters, so it should fit through those. So what we're doing is flooding the permeable flux zones. I'll see if I can make this animation work. It's working. Okay, so what happens is you inject it into the subsurface. It spreads through that flux zone through which the contamination is moving. It then quickly absorbs that contamination, which immediately reduces the off-site liability. So if you're doing on-site work to remove the source, you can shut the door on the contamination very, very quickly. It will then sorb further influx coming from upgradient. It'll sorb influx from back diffusion from low permeability secondary sources on the site, and then it'll biologically degrade that contamination. So you're basically placing a purifying activated carbon filter into the subsurface. And this is what it looks like. You know, you've got sand there at the bottom when you inject the plume stop, which also works this way. The PetroFix, it will coat the subsurface with activated carbon, and it looks like this. So application scenarios: petrol filling stations, where you're replacing tanks. You can put the product into the base to deal with the residual contamination. Also, if further tanks are going in to, if they go, at some point they're probably going to leak, or you're going to have a spill, so you can use it prophylactically to grab that contamination as and when it does leak. You can use it in a barrier application. So you inject the product at the edge of the site and prevent that contamination going off the site. Legacy sites, so these are sites where there's no real money for remediation, there's not going to be monitoring on the sites, but you do have a liability. There is contamination going off the site. So it's a very low cost way of just stopping that contamination moving off the site. You inject it, you start the biological process, and then that continues on. Oil spills into excavations. You can reduce the residual odors from the residual contamination in the groundwater. Where you've got tankers that have tipped over, broken pipes, you can also reduce the extent of the impact. If you shoot it in the ground early enough, you're going to reduce the movement of that contamination. It's not going to deal with huge levels of LNAPL. You will be overcome. It will move, basically sorb to all of the granular activated carbon, and it will be overcome. So if you've got sites where you have continuous high levels of LNAPL, you want to do some primary treatment first, but low levels of LNAPL, high levels of dissolved phase contamination is absolutely fine. Vadose zone treatment, so there is talk about using this under transformers to reduce the impact of oil leaking down towards the groundwater, or you can put it into the smear zone to reduce secondary source flux. Preventative measure, as I mentioned, into underground storage tanks or pipe bedding. You can also integrate it with on-site remediation or as a polishing step after that on-site remediation. Okay, so just a couple of beta sites to finish off. So these are the beta sites on which the product was tested before launch. That barrel there is batch number 1. They're being used in the US on relatively shallow permeable aquifers. With monitoring occurring. So this one's in Panama City Beach, just right next to the beach, as you can see. Not a bad site there. So it was a 4,000 litre petroleum release. There was a limited excavation at the time to get rid of a lot of the contamination from the source area, but there was dissolved phase contamination continuing to move off the site. There've been several attempts to remediate it with limited success. So this was a test site, so basically an injection into this small area at the center of the plume, 10 direct injection points, 770 kilograms of PetroFix was injected, and the concentrations there, there's some BTEC, so not huge concentrations, but still fairly decent concentrations there, 14,000 microgram per liter, TPH up to 15,000 microgram per liter. So fairly decent concentrations. March is the baseline there, and then the injection went in straight after that. So this is last year, and we get straight to non-detect, and then it stays at non-detect from there. So you're taking that contamination out of the groundwater, and then you're biologically degrading that, and that continues. Full-scale application is going to go ahead at any time now on this site. The second site, we have some microbial data, which I'll get into as well. So this is a much larger site. So it's a bulk petroleum storage facility. On that map, that's all of the site. So there's lots of buildings and tanks, etc. on there. There's been LNAPL on this site for a very long time, moving south to north. When they injected the product here, they didn't have continuous LNAPL, but you'll see from the concentrations I'll show you that there's obviously something lurking around here. You know, there are globules, there's a sheen, there is some free phase knocking about. So this is really at the top end of what PetroFix can deal with. So it's quite useful. So they tried LNAPL recovery, they tried SVE on the site, and then they've tried this PetroFix just again around this one well in as a beta test, as a pilot test. So 12 injection points. Similar amount of PetroFix, a little bit more, 900 kilograms. And you see the concentrations there, BTEX, 3.5 milligram per liter. TPH in total is probably about 50 milligram per liter. And I'd say that's getting to the top of where you want to use the product, you know. Beyond that, really, you're going to be seeing continuous LNAPL, and you should be doing something else first, or you could be using PetroFix further down gradient, something along those lines. So this is the top end of the envelope as we understand it to be at this time. So there's the concentrations in May as baseline, injected just after that. And you can see non-detect for a lot of those contaminants and a huge reduction overall in the contaminant mass. We never get the diesel range contamination right down to 0, but it continues to go down. But then you see after about a year, maybe a little bit less, we're starting to see breakthrough again. And I think that is because we just injected this one area and there's this huge mass coming in. So it's just become overcome in this period, but we have had a huge effect over that time. And it is due to the plume, the entire plume is due to be injected with PetroFix this year. Now, we do have a bit more data on this site. We've got some data at the top there for the nitrates and sulfates. So you can see when we inject, the nitrates and sulfates go up. Nitrate doesn't go as high as the sulfate and is removed because it is used so quickly. So that's used to drive the degradation very rapidly. The sulfate, you see it spikes and then degrades very quickly. So we're not leaving high levels of sulfates on the site. They're being used very quickly over a number of months to degrade that contamination. And then you're down to fairly low concentrations after about, what is that? 10 months, 6, 7 months, something like that. Now, if you compare that then to the methanogenesis underneath, you'll see that there was a low level of methanogenesis, low level of methane, sorry, as baseline. We inject, we disturb the groundwater, so that drops, and then we kickstart that biological degradation. So you get an increase in methane production. You're still at very low concentrations. You're not at problematic concentrations here. But as the sulfate and nitrate are used up and gone, you can see that the methane production is continuing at that same level. So we've stimulated that biological degradation, we've kickstarted that biological degradation, and then through syntrophy, these microbes are propping each other up and they're chewing through this contamination. So they're degrading this contamination, this really high level of contamination that is now on the activated carbon. Bear with me if I realize that's an hour. I'm only a couple of slides away. So this is an interesting slide as well, where we looked at PCR testing of the microbes within the site itself. So what we're looking at here are not just the microbes, but the genes encoding for enzymes that break down certain petroleum hydrocarbon contaminants. So you see at the start there, there's a number of microbes and enzymes that we can see from this, but overall, over time, you can see there's a trend upwards. That top line is the total biomass, and you can see that by removing that contamination from the groundwater, we're allowing the biomass to grow. The next line up, the dark blue, is the APS, and that is sulfate reducing bacteria. So you can see we're really stimulating those to degrade the contamination. And then you've got PM1 underneath, which is thriving as well. PM1 is it breaks down MTBE, but it also can break down a lot of petroleum hydrocarbons, and you can see that we're supporting the growth of that beyond where the electron acceptors that we've put in have been used, and this syntrophic degradation is continuing on. So getting some really good degradation there. So PetroFix is effective for petroleum hydrocarbon remediation. There is microbial geochemical data to support the treatment principle. As I say, go to our website or email me and we can give you even more information. And I know I've rushed through that in about half an hour. It gives you lasting treatment, containment possible with very little or no maintenance. So it's a great product for a lot of petroleum hydrocarbon sites that tend to just sit without treatment. So thank you for bearing with me. I know that was quite quick for 2 products, but do we have any questions? Oh, I'm being passed some. So what have we got here? Okay, so concentrations. There's a question about the zero valent ion. The sulfidated colloidal zero valent ion, basically how much zero valent ion is in the product. There's 40% by weight in the product, but that then tends to be mixed either by itself or more likely into an electron donor. So you're generally injecting something like 2 to 10% in the subsurface. Question on bedrock: has the product ever been used? Sorry, question on PetroFix: has the product ever been used in bedrock? It has. Unfortunately, I haven't got any data to show you on that one. It has been injected, I know, and it went in fine. It will have gone further into the subsurface because you've got bigger fractures, so there's no problem in using it in the bedrock. I would suggest using a pilot study on that to see what sort of effect you're getting, and also a good design verification testing, try and find out where those fractures are that you're targeting is key there. Let me have a look. S-MicroZVI valent ion, is it useful for hydrocarbons such as kerosene or diesel? No, you won't be able to treat kerosene and diesel there. You're looking for halogenated contaminants. So you need to move on to either the PetroFix or aerobic biodegradation or chemical oxidation, something along those lines. S-MicroZVI. How much time does it need for the groundwater to be clear from contaminants? Well, that depends on a number of things. That depends on the amount of contamination. It depends on how fast the groundwater is flowing. It depends on what you consider clear from contaminants, so what is your target. For enhanced reductive dechlorination projects, generally you're looking at a 2-year program. When you're using zero valent iron, you should be able to shorten that. But again, it could be that you're using the zero valent iron to target more higher levels of contamination. So you still may be looking at that sort of time frame. You're certainly not looking at weeks. You're looking at a number of months when you're dealing with chlorinated solvents. Are there any additives that prevent substance of iron in the suspension? No, there's not. We don't use any thickening products at all. Because it's there's such fine particles, they're actually slightly more buoyant. So you mix them up on the site and put them into the ground with the glycerol that's in there. They will, float's the wrong word. You'll be able to move them through the formation quite readily. The difference is night and day. The picture that I showed you in the presentation, I wish we had that animated, because with the larger scale zero valent iron, it does just drop straight out of suspension. Whereas this, you mix it up, it's suspended in the water quite nicely, in plenty of time to inject into the subsurface and spread out. I mean, you don't want to mix it the day before and inject it the next day. You mix it there and then and inject it in the subsurface, but you've got plenty of time to get it in the subsurface and for it to distribute nicely. No escape. There's a question on Brexit. Basically, are we able to continue supplying to the UK and or to Europe? Yes, basically. We have stores in Europe, in Ireland and in the UK. And I've been spending many an enjoyable day trying to work out how much product I need where. So basically, I've spread the products across the continent, so we will be able to supply all the projects we know about and upcoming projects until everything settles down. How are we doing, Amanda? Any more? Couple more? Couple more. I'm getting the thumbs up. Okay, so is PetroFix monitoring data illustrated for wells down gradient of the application zone? That is a good question. I don't think they are on the beta sites that I showed you, but I should be able to show you data from that sooner rather than later, because one of the things that people are really taken to using the product for is barrier applications. So obviously the data that you're generally looking for is down gradient. Now, down gradient data is always complicated by the fact that it's not just a wavefront of clean water coming through. You've got the back diffusion from the impermeable zones coming in at you as well. So it depends how far down gradient that monitoring point is. But that is something that we should be able to start showing soon. So we'll continue to produce case studies, put them on our website, put them out on email or other medium as well. Just a question on the longevity of S-MicroZVI line. I don't know whether I touched on that, but it should last about 2 years in the subsurface. Does the black color remain forever? That's a PetroFix question. I'll finish off with this one. Yes, it will do. Basically, once the PetroFix, once the carbon is absorbed to the sand, the silt, the subsurface, it doesn't come off. It's basically stuck on there forever. It's not really an issue. You know, it's just going to be sorbing contamination, allowing biological degradation on there. It isn't going to go too far, so you're not going to see it many meters down gradient, etc. I suppose that leads on to monitoring. When you inject the product and you go to monitor and the water in your well is black, you just want to leave it a couple of weeks until that all settles down, and then take the sample or filter that sample to take the carbon out of the sample itself. I've run 10 minutes over. I'm going to stop there. So if I haven't answered any questions, because I can see there's more questions coming in, what I will do is email everyone back with the answers to their questions. If you think of anything that you want to ask after this finishes, do email over the next day or two, and we will get back to you. If you need any more information, any references, anything like that, just ask. We'll get those to you. But I hope you found that useful.
Thank you, Gareth. That was a great presentation, and thank you for everyone for attending and for sending in your questions. We've had quite a few, and as Gareth mentioned, don't worry, they will all be answered within the next week or so. Within the next hour, you will all receive a short questionnaire to get some feedback, and within that you can ask for an attendance certificate, which may contribute to your continual professional development. So if you would like a certificate, rather than emailing me or Gareth to ask for it, please just submit your questionnaire, and then we have all those requests in one place and we can process them. So thank you very much again for attending, and don't hesitate to get in touch if you've got any questions. Have a great afternoon. Thank you. Bye.